Welcome back again. So this is part D of the chapter 14 on acids and bases. So in this part of the lecture, we're going to talk about how to differentiate between a strong or a weak acid. We will do the same thing for the bases. And once we do that, we're going to determine the concentration of hydronium in the solution. Remember that when an acid behaves like an acid on the Bronsted-Lowry definition, is going to donate a proton to the water, making hydronium. So the formation of hydronium is that tell us that we have an acid. The more hydronium we create, or the higher the concentration, the higher the molarity, the stronger the acid is. So let's see how we're going to do that here. So first thing, we have to know which is a strong acid, which is a weak acid. And that is super easy because there's only 7 strong acids. As long as you memorize them, every other acid is a weak acid. So the strong acids are going to be hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid. 1, 2, 3, 4, 5, 6, and 7. So those are the strong acids. Anything else that is an acid is a weak acid. So which one is a strong acid? That one and that one. That's it. As simple as that. You know the 7 strong acids, everything else is a weak acid. Everything else that is an acid, obviously. So what can we do with that information? Well, let's see. Write a balanced chemical equation that shows the acid is a Bronsted-Lowry acid, so it's going to react with water. Then determine the concentration of hydronium in each acid solution, and decide if the acid is weak. And if it's weak, in terms of having more or less hydronium than what the solution has. For example, let's find first the strong acids. That's a strong acid, that is a strong acid, and the other one is a weak acid. Now let's write the equation for the Bronsted-Lowry, which is the acid, which is aqueous, reacting with water, doing what acids do, that is donate a proton to the water, producing hydronium, and the conjugate base. And make sure you keep track of those charges. And it's already balanced. So the question is, determine the amount of the molarity of the hydronium. So here's the thing. Since Hi is a strong acid, all of it will become hydronium. That's what it means. That if you have a strong acid, every single one of those molecules will become hydronium, or will donate a proton to the water, making the water become hydronium. In other words, since this acid on the first problem is 1.7 molar, and all of it is going to become hydronium, the concentration, the brackets mean concentration, remember that, of hydronium is going to be the same as the original solution. As simple as that. So the formula showing that this is a Bronsted-Lowry acid for the nitric acid, it will be the nitric acid donating a proton to the water, making hydronium, and the conjugate base. Since this is a strong acid, all of this will become hydronium, so the hydronium concentration is going to be 1.5 molar. So it's a relatively easy concept, right? If it's a strong acid, all of it will become hydronium, so the concentration is the same. This one here is a weak acid, which means when it behaves as a Bronsted-Lowry acid and reacting with water, it will donate one of the protons, creating hydronium. However, since this is a weak acid, not all of it will become hydronium. So the way we're going to show that is by saying some of it will come back and destroy the hydronium. So 2 arrows means that you're dealing with a weak acid. So put that in your memory bank. Weak acids are represented with 2 arrows, which means there's an equilibrium on some of them breaking, some of them reforming. So at no time, 100% of them will go the same way the strong acid does. So the only thing I can say about it is that the hydronium concentration, the only practical thing I can say is that the hydronium concentration is going to be less than 0.38 because not all of it will become hydronium. So that's how we deal at this level with an acid being strong or weak in terms of the chemistry that is involved. So you should be able to do this problem now. Remember your 7 strong acids, right? So let's do the same thing with the bases. So there's not a list of strong bases, there's a rule. So all strong bases will have a metal and hydroxide. And this could be different numbers in here. So it has to be a metal with a hydroxide. It's going to be ionic. So let's find our strong bases. Not the first one, the second one, yes. Potassium is a metal with hydroxide. Second one, yes, calcium is a metal with hydroxide. And not the third one. The third one is just a salt. Also, this metal has to be from group 1 or 1A, or from group 2 or 2A, except beryllium and magnesium. So that's going to be lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide, in addition to strontium hydroxide, barium hydroxide. So anything on group 1 and group 2 except beryllium and magnesium with hydroxide is going to be a strong base. So remember that. So can we write a balance equation for the strong bases, showing them as a Bronsted-Lowry or Arrhenius bases? Arrhenius bases produce hydroxide. So the first one is a strong base. So let's find the strong bases first. So that's the only strong base. And it's going to behave like a Arrhenius base, producing this actually should be like that. There was a typo on the textbook. Should be basically the ionic ion dissolving in water. So Arrhenius base produce hydroxide. Since this is a strong base, 100% of it will go. So the concentration of hydroxide is going to be 1.7 molar. The next one is not a strong base. So therefore, we cannot represent it as an Arrhenius base. We're going to have to use the Bronsted-Lowry definition, reacting with water. And that's going to give us, it's weak, so 2 arrows. And that's going to give us bases take hydrogen. And hydroxide will become the conjugate base. The conjugate base of water. And since this is not a strong base, the only thing we can say is that the hydroxide concentration is going to be less than 1.5 molar. It doesn't go 100%. And the next one doesn't contain hydroxide, so it's going to have to be a Bronsted-Lowry base reacting with water. Producing is a weak base, so 2 arrows. Is gaining a hydrogen, which neutralizes the charge, and creates hydroxide, therefore a base. And the only thing we can say about it is that the hydroxide concentration is less than 1.5 molar. Okay, so you should be able to do that now. And once you do that, we can say that we have a very good understanding on how to determine if a base is a strong or weak base, how to determine if an acid is a strong or weak acid. And until the next one, where we come back and we will begin doing calculations to find hydronium given the hydroxide or hydroxide given the hydronium. So that's what we're doing when you come back. So see you soon. Take care.